Hello dear students, welcome to Pen and Paper Chemistry on YouTube. Lesson 5 D and F block elements. Now here what I've tried to do is, we are doing the F block elements. I'm taking the study of lanthanides and actinides parallelly, and in the event we are also doing a comparative account of both of them. So the F block elements are divided into two categories, lanthanides and actinides. Lanthanides follow from lanthanum to lutetium. I know lanthanum is an element of the D block, but because its properties are similar to lanthanides, that is why it is studied as part of this block. So atomic number 57 to 71. Actinides similarly, actinium 89 to lawrencium 103. Writing the electronic configuration in terms of the nearest inert gas configuration, we have 4F1 to 14, 5D, 6S. So 4, 5, 6, whereas in the case of actinides, expressing it in terms of the nearest inert gas, it's radon 5, 6, 7, right? I'm not going to take each and every detail because we've already covered this in lessons earlier. Now, previous lesson number 4, we've already spoken about lanthanide contraction, and the same way we have actinide contraction as well. But lanthanide contraction is more relevant and it is more known because it affects the elements which are following lanthanum in the D block. We've studied also earlier that the atomic size of the lanthanides decreases as we go across. Similar scenarios observed in the case of actinides, and that is why we coined the word lanthanide contraction and actinide contraction. Ionic size also decreases, ionic sizes decreases. These are silvery white metals with low tensile strength. On the other hand, actinides are radioactive in nature. That is why it is difficult to study them in depth. Lanthanides, along with scandium and yttrium, these 17 elements are actually called rare earth elements. Now, can you give me the reason as to why they are called so? Yes, they are not as rare. It's not that you don't find them. You do find them. Then why are they called rare earth elements? So that's the question for today. Go on to density, high density, and it also depends on the atomic number. High density is simply can be explained because the atomic size is decreasing, whereas the mass number is increasing, right? Atomic size, we know that the size of the atom is decreasing. So atomic size decreases, atomic mass increases. We know that density is mass divided by volume, right? That is why they have high density, which is dependent on the atomic number. These also have high density except in the case of TH and AM. What is TH and AM in this? What do these symbols stand for? Which elements do they represent? Their ionization energy is low because of the shielding effect of the F electrons. Similarly, actinides also, whatever little we know, it says that ionization energy is low. In fact, in the case of lanthanides, the first and the second ionization energy is so low that it resembles almost the behavior of calcium in the S block elements, right? We continue with this. Please make a note of these points and your notes are ready for offline reference. Pen and paper in hand, and we go on to point number 7. Seventh point. Lanthanides are highly electropositive, which is quite understandable because of their low ionization potential. Similarly, for actinides, they are highly electropositive. Again, it can be explained. All these points can be easily explained by the help of their configuration. Now, if you remember when we did the D block elements and their general properties, I have discussed all of this. So, if you are unclear about this, please go through lesson 1 and 2. Lanthanides, the most stable oxidation state is +3. Although there are elements which are showing the oxidation state of +2 and +4 as well. Examples are listed over here: europium, ytterbium, samarium. We have +4 cerium, protoactinium, neodymium, terbium, diasporium. Now these are exhibiting +4 oxidation state only in the case of oxides. Now something interesting over here: although there are +2 and +4 forms existing, most of them they tend to revert to the +3 stage. So if they are changing from +2 to +3 oxidation state, that means oxidation number is increasing. They are themselves getting oxidized. If they themselves are getting oxidized, they are acting as good reducing agent, right? On the other hand, if the oxidation number is changing from +4 to +3, the oxidation number is reducing, decreasing. That means they themselves are getting reduced because the oxidation number of these elements is reducing. So they are getting reduced. That means they are good oxidizing agents. For example, cerium, if you see from +4 to +3 state, it can easily change to that. But the reaction being slow helps us to use cerium as, yes, an analytical agent, so that you can observe the rate of the reaction along with its effects. On the other hand, in the case of actinides, we notice a range of oxidation states: +2, +3, +4, +5, +6. And as I said, they are radioactive. Some of them, their half-lives is very, very small. So that is why it is difficult to study their behavior. Because they are highly reactive, they get easily tarnished in air. Similarly, please complete the sentence. Yes, they also get affected by the oxygen of the air, developing a layer of oxide which reduces their metallic luster. We still continue. We are not yet done with it. Oh yes, I am waiting for you to make a note of this. When we talk about the color of lanthanides, now their compounds, in the native state they are usually silvery white in color. But when you talk about the solid or the solution form of these elements in the form of compounds, yes, they do show some color. Reason for this would be the transition, would be the electron excitation due to the absorption of light. Again, we have already covered this concept under the D block element, so I request you to visit that video and make your concepts clear. In the case of lanthanum and lutetium ions, we see that in their compound form, compounds of these two elements where they are in tripositive state do not show any color. How do we explain this? Again, I come back to the chart that we had drawn for the previous lesson. If you notice, lanthanum is 5D16S2. With the result, what will happen is, in order to form the tripositive ion, it is going to lose these 3 electrons. So the rest of the electrons are paired up. Correct? Come to cerium. It has got the configuration 4F1, 5D1, 6S2. In order to form tripositive ion, what will happen is it will lose the 3 outermost electrons. And the F1 in this case is stable, does not want to get excited, it's happy in its own world. There are many anomalies in the case of F block elements which are not still very clear and which we've not been able to explain by the general knowledge of chemistry that we have. But what is interesting to observe over here compared to the D block elements is the narrow absorption bands. In other words, the frequency differences between the colors of the lights absorbed is small in the case of the F block elements compared to the D block, which is very, very obvious from the fact that excitation can take place within the F orbitals as well. Actinides, yes, their compounds show colors. They are paramagnetic, attracted by an external magnetic field. Yes, here the lanthanides also will be attracted by an external magnetic field, except when there is no electron in the 1, 2, 3, 4, 5, 6 and 7, except when there is no electron in the F sublevel, right? We have seen configurations like that. Or when the F sublevel is completely paired up, right? In such a case also they will not show paramagnetic character. Lanthanides, because of their large size, small charge. Why small charge? Most of them are existing in the oxidation state +3. Because of the small charge to mass ratio, they will not be able to form complexes easily. What is happening is their charge is small, their heart may be big, but they don't have enough to give or enough space to take. So with the result, the ligands cannot attach to them easily. Whereas in the case of actinides, we notice that yes, they do undergo complex ion formation. Lanthanides and actinides both are belonging to the F block. In both cases, the electron is entering into the F sublevel. Then why this difference in behavior, such a difference in behavior? Of course, there are similarities, but there are differences in behavior as well. What explains this behavior? In the case of lanthanides, we notice that the configuration, how did we write the configuration? 4, 5 and 6. In the case of actinides, our configuration was 5, 6, 7. Wondering what I am talking about? See the first line that you have written under lanthanides and actinides if you've got the notes in place. Yes, this is what I mean by offline reference. Now this is, let's take a comparison over here. You've got a classroom. You've got 30 students in that class. The students in that class are sitting and they are occupying certain places. Now let us suppose that I add 10 more students in that class. What will happen to the proximity of the students? Will they move further away from each other or will they come closer? Yes, they will come closer. The same thing happens over here. Although the atom has a big space within which it can spread itself, but as the size of the atom is increasing, the energy gaps between the valence shell and the penultimate shell is decreasing. Whereas in this case, the energy gap is still large enough, which accounts for all the differences in behavior that we have seen in the case of lanthanides and actinides. Actinides mostly are radioactive elements. We notice that the actinides in the first half do still have some radioactive nature, which is the half-life is long enough so that we can, probably study them a bit. Whereas in the latter half, what happens is the half-life is very small. They exist for a short time. So the study of their behavior becomes a little difficult. I'm going to give you a flow chart for the chemical reactivity of lanthanides in order to make it easy for you to remember. So please make a note of this and then we go on to the chemical reactions of lanthanides. We are now doing the chemical properties of lanthanides and we are talking about their general properties. We are not taking specific cases over here. Ln stands for any lanthanide and the only thing you have to remember is that the oxidation state being shown by most of them is +3, right? This was one of the points we covered in lanthanides. That means you talk about lanthanides as valency 3 and that's it. You can write the formulas yourself. Lanthanide with hydrogen on gentle heating gives you LnH3, hydrogen valency 1, lanthanum valency 3, Cross, yes. Go back to your class 8, class 7, class 8. That is how we used to write the formula. Lanthanides burnt in oxygen or oxidized by the oxygen of the atmosphere, right? That is why they lose their luster. Ln2O3. With sulfur, what is the valency of sulfur? Very good, it's 2. So lanthanides is 3. So what will be the formula? Ln2S3. Nitrogen, what is the valency of nitride? Think, it's 3. What will be the formula for lanthanum nitride? Ln and a capital N. Please be very careful about where it is a small n and where it's a capital N. With carbon, there are a series of compounds formed which are listed. With water, what will be the product form? Write the product form with water. Go ahead. Take it as HOH. Yes, it's a hydroxide. And hydrogen will be liberated over here. It's behaving like a metal. Can you recall? We compared the lanthanides to which metal? Very good. We compared them to calcium. With halogens, when the lanthanides are burned in halogens, again, what is the valency of halogen? I am talking about Cl. So if I have lanthanide, any lanthanide with Cl, chloride valency 1, this is 3. If instead of chlorine we take bromine, LnBr, valency 1, valency 3. So what is the general formula of lanthanum hydrides? LnX3. They react with the dilute acids. Again, recall what we said. They are behaving a lot like alkali metals, right? So that means they will liberate. Very good. Hydrogen when they react with dilute acids. So they will form the salt and hydrogen. That means they are more or less reactive than hydrogen. Yes, they are more reactive. Their reduction potential is greater than hydrogen. Right? They have more tendency to get reduced. This completes the F block elements for us. We are now left with the 2 compounds of the D and F block, that is potassium permanganate and potassium dichromate. Lesson 6, I shall teach you tricks and tips in order to remember and in order to write their reactions. So stay tuned, stay calm. Happy studying to all of you.